In this lecture, we'll look at density of exoplanets and what we can learn about density and the fundamental nature. Density, of course, is not the same as mass. Density is the distribution of mass, or the mass per unit volume of a substance, measured in units of kilograms per cubic meter or grams per cubic centimeter in the metric system. Mass is a measure of an object's resistance to acceleration, measured in kilograms or grams. So two objects can have the same mass but wildly different densities. For example, glass and lead have densities that differ by a factor of 4 or 5. Lead is more than 4 times as dense as glass, which means in lead, the atoms are packing at the microscopic fundamental level 4 times as many particles per cubic centimeter than the composition of glass. And these are both solids. If you go to gases, the range in densities is even larger. As we've seen, exoplanet density can be measured assuming we have 2 independent measures of the exoplanet, one from the radial velocity method, which is used to measure the mass, and one from the transit method, which is used to measure the size. Of the nearly 4,000 exoplanets that have been discovered so far, roughly 10% of them, or almost 400, have both measurements. So we have had density measurements of some precision for several hundred exoplanets at this point. And this is the most valuable information we can get because it tells us more about what's going on in these systems. However, knowing a mean density, one number, does not uniquely tell us the composition because there are many models that can match a single mean density. There was a lot of excitement in the exoplanet community a few years ago when a small planet was found where the density was measured and the implication was that it could be a water world. A set of small telescopes was used to detect an exoplanet transiting in front of a nearby red dwarf star. The aside here is that not only are we looking for planets around sun-like stars, but we're also looking for planets around dwarf stars. Recall that most of the stars in the Milky Way galaxy are actually red dwarf stars. So if you restricted your viewing to sun-like stars, that's less than 10% of the population. We want to know if exoplanets are a universal phenomenon, and in particular, we want to know if they exist around all types of stars. So only in the last decade have surveys been extended to dwarf stars. In this case, the estimate was that the size of the planet was just under 3 times the Earth's size. A separate measurement using the radial velocity method came up with a mass of about 6 times the Earth. That suggests a mean density of 1.8 grams per cubic centimeter. Compared to water, with a density of 1 gram per centimeter, that suggested the planet might be composed largely of water. If it were composed primarily of metals and rocks, like the Earth, for example, then it would have a substantially higher density, factor of 2 or 3 higher. So this large density, but not large enough to be primarily rocky or metallic, suggested that this could be a body where there's a substantial fraction of its mass in the form of water. Now that's not a total surprise, because in our solar system we know of smaller objects in space where there are almost equal mixtures of rock and ice, frozen. So it's not unprecedented. It was a very exciting discovery when it first happened. However, the planet might have a small dense metallic core surrounded by a large hydrogen atmosphere. That would give the same mean density. However, that was ruled out because the star would then rapidly boil away that atmosphere, so it would not be a permanent feature. It's more likely and most probable that this planet has a core made of solid water or ice because the red dwarf star gives insufficient intensity at that orbital distance for the water to be liquid, and then a small hydrogen atmosphere surrounding, which is expected for a planet orbiting so close to its star. Both of these structures would yield the same mean density. So it's likely out there in the universe and in space and in the Milky Way galaxy, there are many different compositions of planets. Here are some possible planet structures. Some of these have been observed and some not. We'll show an Earth-mass planet or a direct Earth analog, and for comparison in the background you can see the size of the Sun, and then a super-Earth, actually quite a large super-Earth, a 5 Earth masses. And in this case, we see 6 different possible compositions, ranging from high-density planets that are made primarily of metals, to planets that are made entirely of rock, to planets that are made of carbon, which would be relatively light compared to silicates and carbonates in rock, to the pure water world that we saw an example of recently, to gas giant planets, small giant planets, made of carbon monoxide, carbon dioxide, or hydrogen and helium. So these are possible compositions, and nature could in fact have made all of these. And as the exoplanets are studied in more detail, we've started to see an amazing diversity of their mean densities and therefore their inferred compositions. This subject is called comparative planetology, and it starts in the solar system, where we try and understand the common features of the solar system based on similarities and differences between the planets. In our solar system, the primary difference is between the small rocky terrestrial planets close into the sun and the large gas giants further out. A secondary difference comes from composition, where we've seen the condensation curve that describes where different ingredients will condense or be possibly seen in their metallic, liquid, or solid form as opposed to vapor. And so close in, all the way to the orbit of Mercury, we can have the condensation of iron, nickel, and silicates. So expect those solid materials. But that close in, the ices will be vaporized and driven off, and liquid will not be possible. So we don't expect to see water, methane, or ammonia. Only further out, in the colder outer regions of the solar system, are we going to see liquids at the sweet spot, the habitable zone for the Earth, and then those volatiles, as chemists call them, in the frozen form as we move into the outer part of the solar system. So the comparative planetology subject started from our own solar system, where astronomers and planetary scientists wanted to understand the nature of the relationship between the planets and the underlying principles of how they formed and are structured. And here you can see a composite of the cross-sectional structures or interior structures of the terrestrial planets compared to the gas giant planets. So carefully studying the planets of our solar system hopefully tells us about the general situation of planetary structures. And this in turn can inform our theory of how planets form in general and help improve our interpretation of the exoplanet data that's coming in. So in this lecture, we've seen that we can learn a lot about exoplanets from their mean density. But not everything. Mean density is just one number. And planets have detailed composition, differentiation, meaning denser materials fall to the center, less dense materials on the periphery, and of course they're surrounded by atmospheres made of light gases. So we can calculate this mean density, and it's indicative of a very broad categorization of planets, perhaps into gas-dominated, water worlds, rock-dominated, or metal-dominated. But in practical terms, many exoplanets are likely to be composites or complex. And so there's a limit to what a single mean density can tell us.